now Rodrigo Rubira Branco is going to give us a scientific but not academical overview on malware.
Thank you very much. Hello, everyone. So thank you for standing up, for staying here. I know I have like two very competitive tracks going on right now, FX and Raul Chiesa. I myself wanted to actually watch their talks. I know they are pretty interesting, so thank you for standing. So the idea of this talk is to be very informal. If you have questions, just send the questions my way at any time, okay? It's better that way instead of waiting for the end. And if you send me questions, I will give like Brazilian drinks, which is like cachaça. The cachaça is a Brazilian drink. I am Brazilian, by the way. And this drink has two main purposes, okay? The first one is you can actually clean your car motor with the drink. So if you don't want to drink it, you can just clean the motor of your car. And the second purpose, I don't really remember because I killed a lot of brain cells using this drink. So, yeah. So this talk, I will start actually complimenting my friends and people who actually contributed for this talk to actually be possible. So Gabriel Barbosa and Pedro Drimel, two researchers working in Qualys, working in my team, actually helping writing all the code. You guys gonna see there's a lot of code that we needed to write in order to actually make this research possible. So they greatly contributed to that. Ronaldo Pinedo, another researcher working with Qualys, who joined our team a little bit later, but also contributed greatly for the project. Peter Ferrier, researcher working now for Microsoft, which released a lot of different papers on many of those techniques that we're discussing in this presentation. Jurian, by the way, he is here, who wrote SXE and released a paper and gave a presentation, Hacking the Box Amsterdam. Just after his presentation, I dropped him an email asking for a little bit more details on what he did, how he did it, and he gladly contributed and gave feedbacks on how he wrote like his tool, and he put the tool available in open source. That greatly helped us to actually detect the techniques and actually look into all the malware samples if the technique were used before. And also reversing labs for writing the Titan core. They gave that to us, and we use that for unpacking malwares. And of course, to all of you guys that do malware analysis and write papers and write blog posts and contribute with stuff, without this kind of research, community research, it's really not going to be possible to face malware. So I will start saying that I live here, okay, in the Amazon forest. Brazil is very well known for having the forest. The forest is Brazilian, okay, it's not international territory, it's Brazilian territory. But that's not really true. I actually live here, where we have the samba, the carnival, the so famous parties. But we don't party all the time. It's not like people believe. We don't party all the time. The city that I live looks exactly like this, São Paulo. It's one of the biggest cities in the world. So there are Brazilians who work, believe me. So today what we're gonna see is I will explain a little bit about like the motivations of this research, what are the fundamentals of the research, what is the approach that we took for doing it, and how we collected the data. Because if we want to say it's a scientific research, we need to show you the methodology behind it. And we will explain a little bit about the techniques, the research that we created, what is available to all of you after the talk, and give some conclusions. So basically, we all know, and we are all here because there are lots of new threats every day, right? In the malware landscape, we know there is like hundreds of thousands of new malware samples coming out every day. That's just not possible to analyze manually. We don't have enough analysts to analyze malwares anymore. We need ways to automate. And that's why we had two other talks about malware in this conference, and both of them talking about automation, because it's just not possible to do that manually anymore. Still, when we see people talking about automation, when we see in the industry people showing automation, and when we read books and papers about automation, they are automating the analysis of only one sample. So if you look like, for example, Kuka Sandbox and other approaches like that are public, that are available for the normal research, for the usual research. They basically automated that task of analyzing one malware sample. They don't automate the task of analyzing many samples. Yes?
You can do like 1,000 samples at a time.
Yeah,
if you
we
want.
had this discussion by email actually just after the Black Hat. Basically, the guys from Kuko dropped me an email saying, yes, you can actually send many samples automatically for Kuko. But the matter is, it's not an architecture that you have like multiple machines and that you can easily split the samples between multiple machines. You can do that only in one machine. And that's very limited when you're talking about hundreds of thousands of samples.
You can use multiple virtual machines at once.
Yes, multiple virtual machines in only one real machine. You still don't manage to actually analyze like hundreds of thousands of samples in one day with only one machine. So that's the main problem. And when we see like the industry talking about that, it's always like this, right? You read the books and people are like, okay, let's automate one step of the analysis. Or when they talk about automating all the steps of the analysis, it's always like this. Yes, you just put multiple virtual machines. That's not the way you're going to do it. You need multiple real machines. I guess you guys saw the threat grid presentation, and they're building a huge machine, huge cluster of machines to actually do this kind of analysis. And that's a big challenge that we have. The community needs to work on this challenge. Kuko is one of the products that are available, and there are other efforts doing it. But what I want to point here is when we see the companies specifically, the AV companies talking about malwares, it's interesting because in one side they say there is like hundreds of thousands new samples every day, and in the other side, when they show statistics against like 4,000 samples, 10,000 samples, 50,000 samples. They never show statistics against millions of samples they're looking at. That's kind of weird because if you have hundreds of thousands every day, when you expect somebody to show you a statistic and that statistic has some meaning, it at least needs to be some millions of samples being analyzed. And that's one of the motivations for this research. To get one specific field, which was like how the malwares are protecting themselves, and look against like millions of malwares and give the results. And then see if we can actually find something out. We actually did on this research. Before we continue, I will just explain what we look at. So anti-debugging for us, for the context of this talk, is techniques that the malware will employ to actually avoid the debugging process. If I know a malware is detecting there is a presence of a debugger, I assume there is an anti-debugging technique present, okay? Not necessarily the malware will do something evil just because there is a debugger attached, but I assume that has to be true. So if the malware has any way to detect a debugger, the presence of a debugger, I assume there is an anti-debugging technique going on. Anti-disassembly, the same applies like for the disassembly process. If there is techniques used to actually confuse the disassembly process, I assume there is an anti-disassembly technique going on. Obfuscation is what we needed to include obfuscation on the analysis, basically because when we look into anti-disassembly and anti-debugging and all other techniques, obfuscation are actually going after us. We have problems in detecting the techniques present because the samples also use obfuscation. So we also need to actually document and try to understand obfuscation. And anti-VMs are techniques that are used to avoid running or to detect the presence of a virtual machine. All this research started because of the anti-VM techniques, actually, because everybody was like, okay, most of the malware samples refuse to run in VM. Is that true or not? I just see people say, yes, the malwares avoid. We know it's possible to detect the presence of a VM, but what is the prevalence of malwares actually doing it? Do I need to care? Do I need to actually run everything in real machines? Do I need to run everything on virtual machines? Which kind of techniques the malware are employing to detect the virtual machines? So those are the kind of questions that we initially had, and with the time, we extended the research to actually cover other techniques. What is interesting here is if you need to remember anything after this talk, anything, is that knowing if a binary is malicious or not is an unsolvable problem, right? We all know that reduces to the halting problem, and that's unsolvable problem. But knowing if a binary employs protection mechanisms, that's very easy to solve. That does not require a lot of machine power. And with the end result, basically what we figure out is like 90% more of the samples use some kind of protection mechanism. So if we, as an industry, just start detecting the protection mechanism itself, we're going to force the malware authors to stop using protection, because that's a problem we cannot solve if they don't use any protection. But then they will have a bigger challenge, because now they will need to write much more code to create the variations. So I hope we, as an industry, will start detecting this protection mechanism the malware employs and start showing that as malicious behavior in programs, because there is not many real-life programs that employ this kind of techniques, okay? So that's an important message that we discovered with this research. So the objectives of the research: analyze millions of malware samples, share the current results that we find, and keep updating it, of course. And we just, are always analyzing new samples. The idea is like, as more as we can analyze, as better. Of course, we have a limited time amount, so for this talk, we analyze like 4 million samples, and that's the results that I'm sharing. We are not only looking into the anti-RE things, okay? The project itself looks into everything. We create like huge reports. But for the talk itself, I'm just going to show anti-RE things, okay? But we cover much other things. Of course, the detection algorithms needs to be improved. So we are always creating and improving and analyzing the techniques. It's interesting that for this to be possible, we needed to have an architecture. So yes, there is a project called Dissect PE that we created. The project is basically to create an architecture that is open for researchers to access malware samples and to have machine power to analyze malware samples. The architecture was created because we see that many researchers that don't work for the AV industry, they have a really difficult time actually to get access to malware samples, to get access to huge sample data. Sometimes you do have access to one specific sample, but it's very difficult to get a large collection that is meaningful. So we created this project in such a way that we give access for researchers to upload code into the portal, and they can actually see like the code running against millions of samples that we have. The architecture is open, completely documented. So we documented the architecture in an IEEE paper in Malware 2010. We have now 10 dedicated machines, and they are like in 3 different sites. 2 are in Brazil, 1 in German. We receive now 150 gigs of malware samples per day, which is around 100,000 new malware samples per day. We receive from different partners. Most of them are AV companies. So I'm not blaming the AV companies. They actually help a lot. We have nowadays more than 30 million unique samples on the database. So those are the distribution of our partners. They are all around the globe. Of course, we have even partners in Brazil because, well, the project is held in Brazil. The project has a backend which is responsible for actually getting the malware samples, distributing between the machines, scheduling new samples, knowing what are the results available on each machine, running the samples, sending the samples to the machine to be run. And each machine has a dispatcher which gets a sample, it starts a VM, it starts the sample, runs all the plugins, stops the VM, gets the PCAP, gets all the information. We do have both static and dynamic analysis, but for this presentation, I will focus on the static analysis only. So all the results that I'm showing are going to be static analysis. So you're going to see some of the techniques that I documented on the paper are not available on the presentation itself, basically because we don't have a way to detect the technique only statically. All the results that we have, like from the backend, are synced back in the portal, and the portal is available to anybody who actually wants to have access. We support like plugins, so it's very easy to actually add new code for analyzing samples. The plugins are actually responsible for analysis. We capture the network traffic Right now, we don't do anything with the network traffic, but we know there is a lot of researchers doing research with network traffic on malware, so we can share data, of course. And we have like unpacked versions of each malware. So, as I said, the architecture itself don't do anything. It's just distributing samples around the machines, putting the samples to run, and running plugins. The plugins are actually where the intelligence holds. The plugins are responsible for actually analyzing something. They are language independent, so we have right now plugins in Python and C, but we can easily plug like Perl code, Ruby code, or whatever other language you decide if it's not Java, because we don't like Java. The way that the architecture was created was to be very easy for plugging new code. So basically, a plugin is any program that receives as input the name of the malware, which is a binary, and as output gives the analysis. When we plug a plugin in the architecture, we do like all the parsing of the output. So we don't want the researcher to change anything in his code in order to actually plug that in the architecture. So here are like, for example, 2 examples of plugins. They're basic programs, really simple programs. They just need to send the result, whatever is the result, to the standard output. We deal with the output, and we put it on the database, and we show that. And the idea here is, if you are a researcher, and you have, for example, an academic research you're doing, or some idea that you had regarding malware, and you have a code that analyzes only one sample, you give to us, we plug it on the architecture, we run against millions of samples, and we share back the results to you and to the community. If we're not willing to share with the community, we are not willing to actually help you as well, okay? That's very simple to understand. So, the plugin types are basically static and dynamic, but the static plugins are usually executed outside of the VM that the malware is running. But we have exceptions, so one exception is the unpacking plugin itself. As I mentioned, we use Titan Core, and the static version that runs on Linux from Titan Core was released only in this Black Hat, so before that they needed to run on a Windows VM. The architecture takes care of the plugins making stupid decisions, right? So if a plugin hangs or fails or whatever, it's not going to break everything. The architecture takes care of that. And for example, the static plugins, they can be executed before the malware is executed or after the malware is executed. An example of a static plugin that gets executed after the malware is plugins that deal with the network traffic. So right now, for example, we get the PCAP and we split the protocols. So we create like different sessions for each protocol using like Wireshark dissectors. And the dynamic plugins are the ones executed inside the virtual machine itself that runs the malware. Of course, some of them needs to run before the malware is running on the VM. Some others demands to run after the malware. We support both cases. Right now, we only support VMs with Windows, but we're planning to plug soon Android. Since we execute the malware, we capture the network traffic of the malware, and we also make available the PCAPs. The name of the project, Dissect PE, actually came because the initial idea was to actually analyze the PCAPs and do something useful with them. So Dissector is the name of the parser used by Wireshark. So we actually got the name of the dissector. It created the Dissect. So stupid idea. I'm really bad with names. So now starting with this specific research, so these are the fundamentals for the research to actually be possible. But what this research comprises actually. So we used 72 cores, 100 gigs of memory. We analyzed only 32-bit PE samples. So we ignored any sample there were not like 32-bit PE samples. For packet samples, no matter how many samples of the same packet we had, we counted only as one. Because since we are analyzing statically without unpacking, we don't want actually to mask the statistics because there is one packet that is prevalent. So when you look into the numbers, if there is, for example, 3 million of the samples that are like packed with the same packet, we only counted this as one sample. Also, we analyze all the packets that are present between the 4 million samples. So we look into all the packers to know what are the protection mechanisms the packers use, and we created like a top packers representation. And for each of the packer, we look into each of the different versions of the packer, and we also include on the paper which are the protection mechanisms each of the packers and each version of the packer actually use. Because the paper is limited in space, we only release it for the top 10 packers, but we have it for all the packers. So if you have interest in a specific packer and knowing which kind of protection mechanism the packer employs, just drop us an email. It's a matter of a query in the database. For the unpacked samples, okay, we avoided samples bigger than 3.9 megs, and that's only for performance reasons because the connection in the Brazilian backend is not really high right now, so it was very hard to transfer all these samples from Germany to Brazil and then copying between the two different sites for the analysis. So we limited the size to the 3.9 meg samples. So our sample set is basically limited. The bigger one is 3.9 megs. Actually, samples bigger than that tend to be Brazilian samples because the Brazilian banks, they are very complex in the security mechanisms they employ. They have a lot of virtual keyboards and a lot of different ways to identify your machine and the machine connecting. So the Brazilian samples usually are written in higher level language like Delphi. Also, we had one specific exception, which was the Flame malware, just because it's Flame, it's big deal, so we wanted to include Flame on the research. So the static analysis, as I mentioned, is the main focus of this presentation. It improves the throughput. That's why we were able to actually analyze millions of samples. Our machines are not that big, as you see. We're always growing the number of machines. We now have more cores than we had when we started. And of course, the malware cannot do anything. When we're doing the pure static analysis before the malware is even running, we have the advantage. So the idea is try to leverage this advantage and see what can we do. Of course, we needed to develop some dynamic counterparts for some specific detection that is not possible to do statically, but we are not including the results here in this presentation, okay? So everything you see here is static. The dynamic parts are available on the portal. Anybody can just drop me an email and I give an account on the portal. So the malware protection techniques in this work, basically how we created which malware techniques we're gonna look at. That was supposed to be very simple, right? The AV industry exists for 15 years. So I was expecting to be very easy to get all the protection mechanisms that the malwares are using. And that's actually turned out to be very hard. The huge majority of the papers are from Petriferia. Some references in blog, some analysis from specific weird malware samples that somebody saw the malware sample employing a new technique, so the guy documented in a blog, but he was not really interested in the technique. He was more interested in how to analyze a malware using the technique. So it was very difficult to actually create a compilation of all the techniques that we needed to analyze. It was very hard. So in this paper, and by the way, the paper are available in the Hacking the Box page with, I just copied to them. So in the paper, we included a documentation for each of the techniques. And in the end of the presentation, I will give you a GitHub address where you can go and download each of the technique implemented. So that means we basically implemented every technique for the malware to avoid detection. And they are now open source on GitHub. So if you are a malware author and you want to create a super malware with all the techniques, just go to GitHub, put it all together, and it's gone. And if you are an AV company, please start detecting those techniques because we're making it very easy for malware authors to actually use them because we want to detect them using it. Of course, we are always updating it. Just after the presentation, we saw new techniques coming out. 2 days before the presentation in Black Hat, somebody actually got a sample of the Finfisher, and he actually made it available to us. So we find out that the Finfisher was using another new technique that we didn't include in the paper. So we're constantly updating the paper. So the version that you're getting here is different than the version that we made available for Black Hat. And we're going to update it soon with more and more techniques. So always pay attention on the version number in the paper. And of course, for testing the plugins, we had a test bed with 883 samples. Well, of course, initially it was 1,000, but we saw some duplications, so we deleted some. In the end, it was 883. And this test bed is only to see the performance of the plugin that we just wrote, to test the mechanism of the plugin, to be sure that everything was okay. It's not really important. For each of the detection mechanisms that we wrote, we have like 3 possible results. One is detected. That means this technique actually exists on the malware sample. The other one is, of course, not detected, which means the technique is not present on the malware sample, or we didn't manage to find the technique present on the malware sample. And the other one is we have an evidence detected. For the numbers that I'm going to show, for the statistics that we created, we ignored the evidence detected because there might be false positives. And we don't want false positives to change our opinions about the quality of AV products or other things that we can actually deduce the quality based on this research. So, when we analyze the sample, we rely only on sections marked as executable or in the entry point. Even if an executable section is referring to another section, but this section is not marked as executable, we ignored it for the analysis, for the static analysis. This basically means all the numbers you see, they are probably even higher because we actually choosing to ignore things that can generate more false positives instead of include them. So probably we're having more false negatives because of some decisions that we made, but we don't have false positives, so that's really good, okay? So the numbers, when I show you a number, for example, if I show you a number and 80–90% of the malware samples use a technique, there is no false positives. For sure it's 89 or more, okay? It's not 89 or less because we have this kind of decisions on the research. We created like a disassembly-related framework. Of course, we didn't want for each of the malware to run different plugins and each of the plugins needing to disassemble the code. But that was possible just because we were the ones writing it. So we created a framework and we just use it. If somebody wants to add a plugin to their architecture, you don't need to use this framework. You can use whatever you are already using for the disassembly, and I will gladly plug. It's just going to be a little bit slower than what we have because here it's basically the framework does the disassembly and calls back the plugins based on the instructions that the plugin is interested. But that was just because we have 55 plugins for this research. So, executive summary. Basically, I will show here the numbers, right? Because the numbers are very important. And by the way, this is a very famous kids history in Brazil, and I love it. But I'm not a kid anymore. So, from the total amount of samples that we analyzed, which means more than 4 million samples, we have that 34% are packed and 65% were not packed at all, okay? So that's interesting because that shows us the industry looking to the packers makes sense, right? There is a problem with packers, samples are being packed. But if we narrow down that, we start looking that the majority of the packers are UPX, which is kind of simple to unpack. And packers like Armadillo is very prevalent, 6% of the samples, but it's still even if you look at Armadillo, as pack, as protect, famous packers, they still don't actually account for the 10%, which is the detection rate that we kind of miss, right? We see some weird packers Bob Soft Mini Delphi, which is used for Delphi programs, some specific packers. And this is interesting because that shows the prevalence of packers are actually changing a lot. It's not hey, Armadillo is a big deal. It's probably the one that has very interesting technology, but it's not necessarily the one that is used more or more common, more prevalent. One thing is, detecting the packers is something very difficult, right? We have basically 2 ways to detect packers. We have a database with signatures for the packers that we trying to detect, and we also use statistics, basically entropy of the sections to know if it's packed or not. So for some of the packers, we just say, well, it seems to be packed because the entropy is very weird, but we don't know which packer is that, okay? So it's also included on the research. And if you have your own database or if you have more information to share, we gladly will plug it and actually give better information on the packer prevalence. We have like a partnership with the Brazilian banks, and the Brazilian banks specifically, they have like incident chains and malware analysts. All the banks in Brazil, it's mandatory for them to have reverse engineers working in the bank. And there is like a chamber, which is basically all the banks, they created like a chamber of banks. And this chamber is responsible for a lot of regulations and a lot of considerations between the banks. And one of the points of this chamber is actually to discuss security incidents, because as you all know, like Brazilians are famous for writing malwares and robbing people. So we always robbed people on the streets. Of course, we do that on the internet as well. And because this chamber of banks, they actually send us all the samples that they see that specifically target Brazilian malwares. And it's interesting because then the numbers change. So like 50% of the malwares are packaged. And if you look into the packers used by the Brazilian banks, they are used related to Delphi and others. If you want to know, okay, what are the protection mechanisms of the packers? So refer to the paper. And actually, like as I mentioned before, like we really wrote a paper. The paper is like 27 pages, like two-sided pages and small fonts, which means it's a big paper, okay? And the paper does not have the code. The code is on GitHub. So it's a big piece of research. And for each of the packers, you can see like we divided like the versions that we see and the protection mechanisms that the specific packer is using. So you have that for each of the top packers. And as I mentioned before, if you need that for any other specific packer, it's a matter of querying in our database. We have that, okay? But that's cool because you can see that how the packers evolved and what they are including. And you can actually start like knowing that some kinds of protections are available in a packer. And that actually helps us to better understand some statistics that we see the industry talking about. Because usually they say, okay, for example, the majority of samples, they detect VM. Okay, so look into the packers. You know that the majority of samples are packets. If the majority of the packers, they have like some kind of anti-VM mechanism, that means, of course, the majority of samples are actually detecting VM. It's just something that you can see when you have like more detailed data. Good. So yes, please, read the paper, okay? There is much more information on the paper than I will give here. Okay, so please, read the paper. Then we decide, okay, what is the prevalence of protected samples? So samples that employ one of those protections that we detect. So the number is like 88.96% of samples have one kind of protection mechanism. That's pretty cool because, as I said, it helps us to reduce the problem, right? So basically, if you want to perform as well as any AV in the industry, and we all know that the AVs don't actually catch 90% of the malware threats, even more when you're considering the new ones. If you want to catch exactly the same level, you just need to have like 55 different plugins detecting 55 different anti-RE techniques, and you're good, okay? Of course, I'm simplifying the problem. We all know that there is a lot of other challenges that the AV industry needs to face, but there is no excuse to not have it, okay? You're going to say, okay, but normal software will use protection techniques. It's very rare. I am aware only of Skype using this kind of protection mechanism. If there are any other, I bet it's much easier to create a whitelisting for normal software using some kind of protection than to create a blacklist for all the malwares. And it's also much easier to create a whitelist for just the software that use anti-protection mechanisms than create a whitelist for any good software, okay? So it's much reduced problem. So that's interesting. And again, the numbers just go bad for the AV industry if you include the plugins that detect evidence. They are not included here. If we included the evidence plugins, this number 88 is going to go to 96, 97% of the samples, okay? Good. So then we split the anti-RE in the specific categories. And it's interesting because 81% of the malwares use some kind of anti-VM. So apparently, the industry is right. They are telling us the truth. Like You need real machines to analyze malwares, right? You don't need to run on VM. That's why they create and they try to sell you these specific sandboxes for analysis because they are very advanced. Actually, not totally true. 99% of these anti-VM techniques basically detect a VMware using the in instruction. So if you go away from VMware, you use something else, you're good against this 99% of detection. Also, if you look better, you're going to see that they use SLDT, STR, all things that are very easy for you to avoid. Very easy. So these anti-VM techniques, although they are much more advanced, they don't even show in the numbers. So there are, yes, they do exist, but nobody's using them. It's much easier to just detect the instruction, to use the SLDT, not even the SIDT, which I thought it was going to be one of the biggest ones. It's not even considerable in the statistics, 0.06, okay? So that's cool, because that means it's not that hard to create a VM that is bulletproof against the huge majority of the malware samples. Nice. If you look into anti-disassembly, you have like two main anti-disassembly techniques, which is fake jump using static carry and clear carry, and fake jump using XOR. So it's interesting because it's not really just because there are a lot of techniques and they are complex and a lot of malwares are interesting. Again, it's a mistake that we as researchers usually make. We want to talk about the interesting stuff, right? But the interesting stuff, it's not necessarily really prevalent. And this clearly shows the case, right? It's the most prevalent anti-disassembly techniques are very simple, very simple. If you look into the anti-debugging, you're going to see that Microsoft is our biggest enemy in that field, right? Because basically the huge majority of samples employing anti-debugging, they use the Microsoft API to actually identify there is a debugger present. It's quite cool, right? It's like, okay, if you really want to actually do something well, just remove that API and like put that as an option if you want a developer machine or something. So when you break down the categories, you start seeing that like the problem is not as hard as everybody's painting. And if we start detecting the techniques itself, and well, there is more techniques to be detected. I will show some of them that we detect and some that we still don't detect. We still need to write detection for them. But if you start detecting those techniques, and that's, again, the main message of this talk, if we start detecting the protection mechanism that the malwares use, that's a much simpler problem than to say if a code is malicious or not. It's to say if a code employs a specific technique. That's much simpler to do. And then we're going to force the malware authors to not protect. And then instead of wasting a lot of analyst resource actually look into samples that are protected, because they are nowadays the problems you can clearly see, right? You will use this analyst time to actually look into more interesting stuff, and you will be able to automate much more things. All the research that we see here, for example, like Stefano's research, they needed the unpackaged samples to actually do some good analysis, right, to categorize. And that's true. So let's force the malware authors to not use those techniques anymore, because if they use, it's easier for us to detect them. I don't know why we are not detecting right now, actually. So obfuscation, the same. Like usually, the obfuscation technique, the most prevalent obfuscation techniques are really simple. So instead of calling, they do a push and a ret, a push, a pop, and a mathematical operation to actually force a specific path, not sequences, like to make it more difficult to analyze. Very simple obfuscation techniques. They are like the most prevalent ones. And that's interesting because that actually helps us to do some other research, because now we can build other research just counting on the fact that, okay, for example, there will be no function call obfuscation other than the very simple ones. So if we want to look for a function call, we can just look into that. We don't need actually to care anymore and to try to create very weird tricks, very specific dynamic analysis for that, because most of the malwares don't use it. And if a malware starts using it, we're going to know it. And then we're going to detect because it uses the protection. So it makes life much easier. So for this research, we actually studied and documented 33 anti-debugging techniques. We currently scanning samples for 31 of them. So those are the techniques that we studied. And important, for each of the techniques, we wrote in the paper a section specifically explaining the technique. And in this section, you're going to find the GitHub link, which implements the technique. As I mentioned, a lot of the materials on the web were not really complete. They had like small mistakes, and they usually don't have like a really real example that you can actually try and see how things work. So we implemented each of these malicious techniques as well. We implemented the detection, but we also implemented the malicious. And in the presentation, you're going to find the section of the paper for each of the techniques. And in the paper, you're going to find the GitHub link for the specific program that implements the technique. We implemented in C and assembly. So the techniques that use like higher level Windows APIs, we implemented in C. The techniques that use assembly stuff, we implemented in assembly. So those are the anti-debugging techniques that we detect. As you can see, there are some that we don't, some that we detect evidence, but we don't completely detect. That's why in the statistics, you'll see some of them, but some others you don't see, because as I said, if we detect evidence, we don't show that on the statistics. But if you really have interest in a specific technique, it's just a matter of talking to me. I do a query, and I can get you the numbers very easily. For the anti-disassembly, we studied 9 techniques and the variations. There are not really a wide range of techniques available. They are very, very limited. So we implemented 8 of those 9. And those are the techniques that we implemented. And those are the sections of the paper, and the same applies here. The paper explains the technique. The paper has a reference to GitHub, where you can get the code to implement that specific technique. The same for obfuscation. Obfuscation is the one that we're lacking more of the implementation and detection, just because we saw the need for the obfuscation later. And that's also a reason that I mentioned to you, the numbers are just going to be even worse for the AV. So instead of 88%, it's going to go to 97 or something even higher of the malware samples using some kind of protection. And those are like the techniques that we look for in the obfuscation. The same here, section of the paper pointing to the GitHub. And anti-VM techniques, we studied like 7 different techniques. We're currently scanning for 6 of them. And those are the techniques that we specifically looking for. As you can see, we didn't care about like a registry names for anti-VM techniques, because looking for a registry string or looking for binaries are very specific to one specific vendor, and we don't believe it's useful anyway, because even in the Sun's guide to how to create your VM, they teach you how to not create a VM that can be detected. So what is interesting is we do understand the malwares are changing. The threat landscape is changing really fast. So just before our presentation in Black Hat, Jurian gave a presentation in Hacking the Box in Amsterdam, so it was on 17th to 20th of May. The presentation in Black Hat was in June, and there he released a SXE tool, which is basically a tool that gets like an x86 binary, and will try to transform this binary to the equivalent binary using SSE instructions. So this is a very interesting way to obfuscate a binary and to avoid the detection by static analyzers, right? So he released on May. In June, he shared all the information, which was great. Without sharing, it's not possible to actually evolve, right? So he shared all the information. He shared the code that he used for the SXE. So we were able to create actually samples using the SXE, and we were able to actually create a detection for the usage of SSE instructions, actually replacing x86 instruction. And we looked into our database to tell that it's really a new technique. The malwares were not implementing it. Maybe they will now that he released it, and we already have ways for detecting. The other one that we wanted to look is the Flame, because Flame, it was big news, and if you were giving a malware talk, you need to talk about Flame, right? So basically, the industry said it's completely new. It uses Lua embedded scripting. So we decided, okay, why not writing a plugin to detect Lua embedded in malware code, and then we can actually find a lot of variants of Flame. And we did it. Flame is indeed the only malware that we saw in our 4 million samples that uses Lua. And indeed, we managed to actually get different components of Flame in that way. And on September 18, Flora Liu posted on the Symantec blog that they found a specific malware using Google's Go. And they said it was new, so we decided to actually write a plugin and see if it was really new. And again, that's interesting because we can detect new samples using the language, and we can also detect the variants right now because there's no other samples using it. So that's the advantage of having an architecture that is very easy to plug and to reproduce whatever research you want to reproduce. Still talking about new techniques, on July 25, Morgan Marks and Bill, they released a paper on the Kingfisher spy kit. And it's interesting because the Kingfisher is top-notch, right? It's like spy kit, it's like military grade, intelligence, all that words that everybody talks about. So they wrote a paper about the Kingfisher, and they shared the binary with us, and I was able to look into the techniques that the tool used. And actually, from the 5 techniques that Kingfisher used for avoiding detection, 4 of them we already catch. Okay? One of them is specific to OliDBG, and the 4 others that are more generic, we catch. So that means if you had an antivirus that actually detects malware trying to avoid detection, or code avoiding detection, you could catch this very advanced military grade, whatever naming people gives to that, okay? So this shows that it's very interesting to actually go for this approach, because then you make the life of the writer more difficult and the life of us analyzing the malwares more easy. And you know, I'm a Brazilian, I like to have an easy life. So some resources. On GitHub, you have all the code for the malware sample, for the techniques that we implemented for the malwares. On research.dissect.pe, you have the updated version of the paper, the presentation. Also in the Hacking the Box website, you can get the latest version of the paper and the presentation. We're gonna keep updating it. So the paper has a version number. We're gonna keep updating the version number. The GitHub is going to be still Black Hat 2012, but we're still updating it when we create a new detection. We also create the implementation for the technique itself. So we're gonna keep updating also the GitHub, okay? So go ahead, download the resource, drop me emails, drop me ideas. Without sharing, it's not going to be possible actually to evolve and solve things. The portal for Dissect is www.dissect.pe. The portal has authentication, so you need to drop me an email in order to get an account. And I will happily share access for you guys so you can see all the statistics from the paper. Actually, it's a huge page with a lot of graphs for the statistics. And just to conclude, so people can actually send questions on my way. For this research, we analyzed millions of malwares, okay? So 4 million of malwares. And for then, we try to detect the protection mechanism that the malware employs to avoid being detected. I have this argument that if you try to avoid detection, you make the detection easier. The same, in my opinion, applies for forensics. As less as you try to avoid to be spotted, as more likely you are not going to be spotted, because that's a problem very difficult to solve, if a given program is malicious or not. As soon as the malwares, the prevalence and the huge majority of the malware, they try to avoid analysis, they haven't disassembly, they haven't debugging, they haven't VM, they're making actually the detection easier. So we need to start detecting that. So we're gonna force the authors to actually fall back to pure malware, and that's going to be much more difficult for them to release new versions, like new variations, because there will be no packing anymore helping them. There will be no anti-protection mechanism that they can just change instructions and things like that to actually protect them. So we're gonna make their lives more difficult, and then we're gonna have an advantage, maybe. Maybe not, maybe they are going to outsmart us again, but probably not, okay? So I really hope people look into that and put a little bit of effort and also see the problems, because I'm sure there are many problems on this as well. as well. So that's what I have to show, and I'm open for questions. This is my email, this is my Twitter or whatever, and feel free also to ask questions here because you want to earn the cachaça. Remember, it kills your brain cells. That's cool. It's good. It's alcohol. And you can also make caipirinhas with that, okay? You just need lemon, sugar, and ice. No questions at all? Ooh, interesting. I am really clear, huh? My Brazilian English is perfect, I see.
Come on, guys, shoot the questions. Don't be shy.
So I will need to drink the drinks.
Oh, here we have a question.
Megabyte.
The only reason...
Any hidden specific reason that maybe...
No hidden specific reasons, even more because there is no hidden commercial expectations as well.
Because you put the exception on the flame malware as well.
Yeah, well, the flame was just analyzed because it's famous, so I wanted to show something about like, hey, this is like top-notch, very, very latest APT or whatever you want to call it. So that's why I included. The limitation was just because to transfer all the malware samples between all the machines, like we had like not really a lot of time to do all the research, and I wanted to show a big amount of samples. Since the huge majority that are bigger than 3.9 megs anyway are the Brazilian ones, we just look at that to get the Brazilian statistics and not actually to get the overall statistics. So that was the only reason, performance itself. But yeah. Much more important question is how did we select this 4 million samples since I said we have 30 millions? It was like really random.
Okay, one question, Rodrigo, here.
Oh, okay. Are you allowed to ask questions?
Yeah, actually I'm...
That's a very open conference, I see.
I'm SVC approved, so... The question is, are you in touch with some people doing open source antivirus to integrate actually these anti-debugging techniques into the detection engine?
Well, if I am in touch with anybody developing open source antivirus to actually integrate that, Sourcefire actually is responsible for Clamavi, which is an open source antivirus. And they are a partner, so they have access to the research. Actually, everybody has access to the research since it's public even more now, right? So I'm not in touch pushing anything, even more because what do I know, right, about whatever are the priorities they have for the project. But yeah, I guess I should maybe write a patch for them, right? Because it's open source, so I cannot blame the open source ones. I can blame the closed source ones, though.
Thank you for the very interesting presentation. I have a question. I'm more interested in the, let's say, state-wise malware. So have you checked what would be the results on Flame and on FinFinisher and stuff like that? If you would detect these malwares?
Yeah. So for the Flame, I forgot to put it here, but like for the FinFish, it's here. So FinFish implements like 5 of those techniques.
Yeah, I saw it, but have you tested
4.
it? Did you run your tool and see if it is detected, if it's picked up?
Yeah, 4 of them.
Okay. Just know if you just looked, okay, this is what is documented, and yeah, we would do it.
No. Yeah, like one of them we don't detect because we didn't know about this technique. It was like 0 day or whatever. Maybe it's documented in weird forums. As I said, it's very difficult to get all the techniques. So if you have some that we're missing, send my way. And 4 others is completely documented, and we already have detections, and we found it in FinFisher. So it was possible to detect FinFisher just using this.
Okay, thank you.
We have a question there.
So there is more questions than cachaça.
Over
Sorry,
here.
because we drank some cachaça on the debate early in the morning.
You mentioned that you limit to one executable section or something like that. So if a malware was to do the anti-debugging stuff in another section, you wouldn't detect it.
Okay, so the question is, if I am limited into only one executable section. No, I am limited to sections marked as executable and the entry point. So yes, if the malware uses anti-debugging, and the anti-debugging is a section that is marked as non-executable. This will run if there is no DEP, right, anyway. But I am not going to detect because I am not going to analyze right now. Yes, that's true. For these statistics, that's true. But that's a limitation that it's just a decision for the test. And as I say, that's one of the things that will also grow the number of detections. Instead of making it more beautiful to the AV vendors, it's going to be even uglier. By the way, it's pretty easy to avoid this limitation, okay? You just look into the entry point and executable sections and see if they refer to other sections, and then you disassemble the other sections. That's not supposed to give a lot of false positives, but I had no time for the presentation to actually include it, and I was afraid of starting getting a lot of false positives and needed to redo everything again, so that's why the limitation.
No more questions? So let's give him a round of applause.
Thank you, guys.
Deserved.